Morning sessions. We have Professor Popescu from the University of Lille. He will be speaking on generalized plumbing and Murasugi zones.
So thank you very much for this invitation. It's a great honor for me to celebrate the 60th birthday of a great person like Pepe. I remember the first time I met him, I saw the appearance of an energetic, big smile, and since then I'm always smiling when I think about him. So I hope that my talk will make him also smile. In this talk I will first start explaining you the background, the historical definitions of plumbing and the Murasugi zones, and then what was the problem we tried to solve and how we solve it. So it's a joint work with Burak Özbakçı from Koç University in Istanbul. Let's start with standard use of the term plumbing. It refers to two related settings which originate in works by Mumford and by Milnor. In following Mumford, it is a cut and paste operation. So first you have to see in your mind, just move from valuations and algebra to the world of topology. And not set theoretic topology, but geometric topology, which extends the Riemann building of surfaces starting from the plane, cutting the plane into pieces, multiplying the cut pieces as Jesus in as many copies you want, and then gluing them. That was a prototype of cut and paste operations in topology, which may be done in arbitrary dimensions. So here, following Mumford, one has indeed both to cut and to paste. In order to describe what? Well, boundaries of tubular neighborhoods, but not only of one submanifold of a bigger one, but of several submanifolds which intersect. Therefore, their union is not a manifold, it has some mild singularities. One can also describe the tubular neighborhood itself, not the boundary. Then one may do this only by pasting, not by cutting. And this is the use of the word plumbing, which originates from Milnor's works. In what follows, in fact, we will be concentrated in this second interpretation, Milnor type plumbing. The original works are differentiable manifolds which are homotopy spheres, which is an unpublished paper of Milnor, which was finally published in his collected works in the third volume of them in 2007, but was widely circulated. This seems to be the oldest paper in which one sees a plumbing operation. And the second one, in exactly the same context, by David Mumford, the topology of normal singularities of an algebraic surface and the criterion for simplicity, where the main result says that one cannot build a counterexample to Poincaré conjecture looking at links of isolated surface singularities. There he introduced, in fact, a description of the link as a plumbing operation, which is a cut and paste operation. One of the first definitions of plumbing in a textbook may be found in Hirzebruch-Neumann-Koh's Differentiable Manifolds and Quadratic Forms, published in 1971, but which develops a course given by Hirzebruch around 1962, so just after the appearance of those two previous papers. The definition is here, it's just copied from their book. One starts, in fact, from two objects which are disk bundles over spheres. So these S1n and S2n are two copies of an n-dimensional sphere. P1 and P2 are the bundle projections. E1 and E2 are the total spaces. In order to plumb them, well, one has to plumb the total spaces of the projection. So in fact, a fiber bundle is much more than a formal definition. According to what we want to do, we can think about it from the base, and from the base one takes sections and one sheafifies taking sections, and then one does homology and spectral sequences and a lot of algebra. But one can also think about that starting from the total space and imagine that one is a fish in that ocean, which is a total space, and looking at what happens there. And this is what we will have to do here. We have to be concentrated on the E1 and E2 points. And we will take apart of those two spaces. In which way? First, in each sphere, take an n-dimensional disk, which is identified to a standard n-dimensional disk, in both of them. And in each case, look at the pre-image of the bundle over that disk. As we are over a disk, the bundle is trivializable there. So that pre-image, which is this part, can be written isomorphically as a product of two n-dimensional disks. Then one has two such products, and one can choose coordinates x and y always by taking the x coordinates inside the base and the y coordinates inside the fiber, as in the usual drawings we do in high school. X is like this and y is like this. So one has two times such a coordinate system, and one groups them by permuting x and y. You see here one has x, y, and y, x, which have to be grouped. Seen like this for the first time, I'm not sure that everybody imagines something. That's why the definition is followed by a drawing in that book, which is this one. So in fact, my preference of explaining mathematics would be to start from the drawing. And I try to explain to other people that if they start as I did now, from a formal definition, I cannot imagine anything. But we have very different ways of thinking, and I think in this book it's perfect because both appear at the same time. So each kind of imagining mathematics is happy with that page, because one can look first at the picture or at the formal definition. So here what you have to imagine, look here, this is a total space of a disk bundle. In this drawing, the sphere is one-dimensional. We have just to imagine here a central circle. The fibers come vertically like this. You just take here a segment inside the central circle, and the pre-image of the bundle over it is this rectangle here. The same rectangle appears in this second total space. But you see now that the rows of zero section and of fibers are interchanged. This is a fiber here, but it is a zero section here. And this is that exchange of x and y rows. In fact, in Milgram's construction, one did once such a plumbing, but developing what he was doing, an industry to understand exotic spheres, one has to recursively do plumbing. So this is just an elementary step, like a summing operation. You know that if you did 1 plus 1, in general it's useful to continue. Here it's the same. So let's continue. Around the same time, Murasugi was studying knots and links in the three-dimensional sphere. So what's the difference from the context of what we just discussed? Is that we were in higher dimensions, and the previous drawing had to be interpreted as a schematic drawing. It was not a surface, it was an arbitrary dimensional plane. Here you have to interpret this really in front of your eyes in three space. This is a prototype for Murasugi's construction. It's like an atomic disk. It's what he called a primitive S surface of type N1. It's very easy to build this with children. You start from two disks. You can make them in paper, and then connect them by some bands here. N is a number of such bands. And you have to be careful to twist them always in the same sense. How you can see this in the picture? Look here at the left strand. The left strand passes here above the right one. And just continue here, you arrive the left strand above the right one, the left above the right one. So So you put any number of bands there. It means that you have to imagine that everything here is field. It is a surface with boundary in three-dimensional space. These are the primitive S surfaces. Using them, Murasugi, 1963, said that one can build more complicated surfaces. For instance, the one you see here, where you have three disks, two bands between these two, and two bands between the other two. It seems that there is a symmetry 2 and 2, but be careful, you see that here is not the same twist. Here is the right strand which passes above, and when you pass here, it's the left one. That's why one has in fact two kinds of primitive surfaces, one of type 2-1, as he calls them, and here of type 2-1. This sign allows to describe precisely the kind of twisting. And here's the operation is simply to start from this surface taken alone, this second surface taken alone, and glue them along this disk. So as in this drawing, you see that the upper one lies behind, and the lower one has to be interpreted as seen from us, as lying in front of us. He in fact iterated this, starting from several number of primitive surfaces and gluing successively along disks. And he showed that like this, one could understand the new properties of alternating knots and links. And it seems that in the 60s, this direction of research did not have a lot of descendants. Till the end of the 70s, when Stalins, in a paper in 1978, generalized Murasugi's construction. He said, why to start from such specific surfaces as the primitive S surfaces? In fact, you can start from any two surfaces in the three-dimensional sphere, and then you can glue them as Murasugi did, by identifying disks. And here is his definition. And what I would like to make you see in this definition is that starting from the second line, everything is abstract. Here T1 and T2 are surfaces. And in each one has a disk. A two-set is a disk. And one takes a diffeomorphism, or here an orientation preserving homeomorphism, which identifies them. And then one identifies T and glues T and T1 by identifying the disks. By H, such that the result is a two-manifold. And then comes the condition. What does it mean that the result is a two-manifold again? It is this. I will show you with a picture what means this relation.
What is a fiber surface?
So this is a very good question. I told you that these are abstract surfaces if you start reading on the second line. But you read the first one. And you saw there precisely the point which makes them embedded. In fact, Stalins was interested in understanding surfaces which may be extended to open books. It means that it is a surface which is a page of an open book. I will come back to open books. Only for people who know this, the main theorem of this paper of Stalins of 1978 was the following one. If T1 and T2 are fiber surfaces, and you do such an identification, such an embedded plumbing, then the result is again a fiber surface. And he gave a very nice corollary in the line of Murasugi himself, who studied such surfaces in order to study links. He applied this to links corresponding to braids. He showed if one takes a homogeneous braid and the associated link, then this binds a fiber surface. So what does it mean? Here is a picture. Please just concentrate first on this part here of the drawing, on the left. Here is a usual representative of a braid. And then one joins the ends on both sides in this way. This is a standard way to pass from a braid to a link. This braid is very special. It is homogeneous in Stolin's sense. Look, here it is standard representation using the standard generators of braids. Those letters correspond in fact to crossings. Each crossing here, and you see 4 of them, correspond to a letter. And you see there are 4 letters. Here, we will have to read this sentence from right to left, like in the composition of functions. Look at the first letter, sigma 2. We will read also the braid here from right to left. The first crossing we meet when we go in this direction is this upper one. This is sigma 2. Then you see here you meet sigma 1 minus 1. Well, because in this direction when you move, the second one you meet is here. And you see, here they are not of the same kind. Here you have this one coming from upper left passing above. Here the parallel one passes below. This is the reason of having here exponents plus and minus 1. But then you see, you get again sigma 2, and again sigma 1 minus 1. What is important is the same letter appears always with exponents of the same sign. So sigma 2 has all exponents positive, sigma 1 all exponents negative. You extend this definition to any number of generators, and this is in general a homogeneous braid, which means that on such a drawing, if you travel between 2 different lines here, all the crossings you meet are of the same kind. And on the next one of the same kind. And if you have more strands, each time you travel between 2 of them, you meet crossings of the same kind. Stolin's theorem is that such a braid is the binding of an open book. That is, it is a boundary of a fiber surface. So the proof is extremely simple from the visual point of view. Here one does the following. You see that when you close the braid, you drew big rectangles which jump to the eyes. Here you see 3 rectangles. And here in this drawing, it is as if we lie above the rectangles, and we see a small one, and then a second larger one, and a third bigger one. Now just move around and look laterally. It is a viewpoint we have here. And just concentrate on this rectangle above and the one in the middle, these 2. And here the crossings can be seen as these 2 bands. So, this link, you feed it by a surface, by first putting here the rectangles, which are 2-dimensional pieces of surfaces, and then connecting them by bands. You will take these 2 bands between these 2 rectangles to build this surface. You put those 2 bands between the 2 next surfaces, you get a second surface. Here I hope that you recognize Murasugi's primitive S surfaces. So in fact, what's happening here is a second description of the example before of Murasugi. Again, you see here appear the pairs 2 minus 1 and 2 1. But here in a much more general context, where you see precisely that from the viewpoint of braids, what is important is homogeneity. And here one has to do is just identifying those rectangles. So here, Stolin's needed a name for this general operation. But he still did not use such a name. And a few years later, Gabai coined the name Murasugi-san for a slightly restricted operation. So till there, the operation was done, but without any name. Gabai needed a name. Well, why? Because at that moment he proposed a general plan of studying this operation. He proved different instances of the following slogan: the Murasugi-san is a natural geometric operation. And he proved naturality in several ways, showing that one has Stolin's-type theorems. If you start from 2 surfaces which have some geometric property, the tendency is that the sum has again the same geometric property. For instance, If the two initial surfaces are incompressible, the result is also incompressible. If there are leaves of some special types of foliations, the sum is again a leaf of that same special type of foliations. And in fact, he discovered other such instances of this motto, and he published a second paper, which is called the Murasugi sum is a natural geometric operation 2. So this is a part of the story dealing about embedded plumbing till the mid-80s. In the mid-80s appeared the first generalization of this Murasugi sum in higher dimensions. In several papers by Daniel Lines, here is a definition. I won't spend a lot of time on it. I want you only to see it. I copied it from the initial source. That you are indeed in higher dimensions. But the fact is that the surfaces which are summed are of a very special type. They bound simple nodes. They are K-1 connected Seifert surfaces, and 1 dozen identifications of pieces which are again, as in abstract plumbing, products of 2 disks. And here is a precise way of doing it. Why? Because Lines treated this operation algebraically. He proved things about the fundamental group and the homotopy type homotopically by doing algebra. With Burakov's Bakchi, at some moment we were discussing about this operation, and we were complaining that in fact we do not understand really any proof of it. And we wanted to apply it and to have a better geometric understanding, in particular without any algebra. Really to see what happens there. Do all the time cut and paste and see spaces, not images, not algebraic images of spaces. So we said what means to develop a more flexible tool? It means what is the most general kind of plumbing operation, meaning abstract plumbing, such that if we do embedded plumbing, Gabai's motto holds. So it means if we do embedded plumbing, again we get a natural geometric operation. And in particular, we said what should be the crucial theorem, which was the one from which also Gabai was starting. We wanted to prove that if we do a generalized sum of leaves of pages of open books, then we get again a page of an open book. And we figured out that in fact we did not have to restrict in any way the pieces of manifolds which had to be identified. Till then, people were in fact concentrating on products of disks, or at least in disks. We said there is no reason for this. We have to be able to take any manifold and identify it. And what we saw is that indeed Gabai's credo comes in this abstract generality. You don't have to impose anything with the exception of the fact that you want to remain inside the manifolds. So the crucial definition is that when you do abstract plumbing, you have to get a new manifold. And then what is representative, what are the types of objects which can be plumbed? Well, you start from any abstract manifold M, and inside it you will isolate some submanifold P, which we call a patch, and the pair MP we call a patched manifold. And things which should be identified are the patches. Here we represented this handle only to show you that you may have topology inside this, that it does not have to be a disk. And the important point is that the boundary of the submanifold lies part inside the interior of the big manifold and part on the boundary of the big manifold. So you see here the red parts are the ones on the touching part of the boundary of the patch, because we imagine now that everything was built in the following way. You take the patch and its complement and you attach both along A to get the big manifold. So you imagine this starting from the patch and doing a gluing operation along A. And this is important, in fact, when dealing with this, because all the game and the conditions which allow you to plumb are easily expressible in terms of this attaching part. And so which is a condition? Our generalization of plumbing looks very much like the initial Miller type plumbing, but you don't have disks, you don't have products of disks. P is anything, like in this picture. And simply you take two abstract manifolds, and we denoted this abstract plumbing operation like this, a sum and a union, because in fact it generalizes something which is classically called a sum, but that theoretically it is a union. Each one of the two terms is included in this one, so it is also a union. And what is important is a piece over which you identify, and that's why we wrote it above the sign. And here you see the main hypothesis. We want the result to be again a manifold, and this means that the attaching region here of the first one, which is A1, the red one, and the attaching region of the second one, the blue one, should be disjoint. And now if you see this, you see that you can extend this to a sum of 3 or 4 or 5 if you identify the patches. Which means that if you do a sum of several manifolds, what is important is that the attaching regions are pairwise disjoint on the boundary of the patch. And that you get an abstract plumbing, which is a commutative associative operation. So this is abstract. Let's pass now again to the embedded operation. Okay. But before passing to the embedded operation, I want to make only a small observation which won't be useful just now. It's just to prepare your minds to use it at some other moment. I told you that you have to identify the two patches. In fact, what you can do is to desymmetrize that operation. From one of the two manifolds, just take out the patch. Here is M1 minus the patch. It's this part. You cut and you remove. The second one remains unchanged. And now you will glue M1 minus P to M2. And you see that you get the same result as before. And you can also do the same desymmetrically by saying that you take M1 and you remove P from M2. And at some crucial moment, this will be extremely important that the result can be described in these 3 ways. So embedded summing. Well, in order to do a drawing, we are obliged to represent surfaces in C3. And that's why here we represented the patch as disks. But you don't have to imagine that they are disks. They are again arbitrary patches. They may be surfaces of arbitrary genus, arbitrary number of connected components in the boundary. So what you do is now M1 and M2 are to be embedded in some ambient space. And what you will do, you take the patch and you move it in the ambient space transversally to M1. Here appears a crucial hypothesis. You have to be able to do this, which means that M1 has to be coorientable along P, not necessarily globally coorientable. That's why here in this drawing we represented a Möbius band in 3 space. A Möbius band is not globally coorientable. But if you take this small part of Möbius band, it is coorientable. And now as part of the structure, such that the operation is well defined, you also have to choose coorientations transversal to P in M1, transversal to P in M2. And then here appears a dissymmetry. When you do the sum, W1 with W2, W1 is the ambient space here. M1 is a hypersurface inside. W2 is the ambient space on this side, M2 is a hypersurface on this side. You have to coorient the patches on both sides. And then do a product here. This is a small solid cylinder. You multiply this patch by a segment, and you remove this from this ambient space. Do the same here, but on the opposite side. So you see that here you remove on the positive side with respect to the chosen orientation, here you remove on the negative side. And then you created some new boundaries. You see that the new boundaries are canonically diffeomorphic because they are the boundaries of the patch cross a segment of a cylinder. You have a diffeomorphism, you identify through that diffeomorphism such that this patch gets glued to this patch. And you get something like this, and the two initial coorientations along P get glued, and you get again the same kind of object, a hypersurface with the same P appearing as a patch inside, and you have a coorientation along the patch. So you see that this is the well-defined new operation. So this allows you, for instance, to plumb Möbius beds in space and to do any kind of construction with them. But what is interesting is that you get now a difference from the situation of the abstract summing. I told you that abstract summing was commutative and associative. Well, now it's not the same. It is still an associative operation, but embedded plumbing is not commutative. So in fact, one has to be careful when writing the operation. From this viewpoint, it would have been better to choose as a sign a product, but we decided to keep with a tradition which called Murasugi sama sum, not products. But one has to be careful in the way of writing. But what's good is that if you want to iterate embedded summing, you may get rid of parentheses because things are associative. So you have only a problem of commutativity, not of associativity. And let's come now to the special types of hypersurfaces we will want to plumb, pages of open books. In fact, open books are objects with generalized polar coordinates, seen geometrically. Think about C, the complex number. Seen geometrically, it's a plane with a point drawn there. Polar coordinates tell you that you have to imagine there that you have a web with all the rays getting out of the origin and all the concentric circles. Get rid of the concentric circles and imagine only the half rays going out from the origin. That means that you have a special submanifold of codimension 2, which is the origin. And then you will have hypersurfaces which get out of the origin, which have the origin as a boundary. And they make the fibers of the vibration. So this is in general an open book. You have some submanifold of codimension 2, which is the binding, the ambient manifold. And outside the binding, you have a generalization of the angle coordinate on C with images which are arguments which go to S1 and which is a local trivial fiber boundary. The pre-images of a point of S1, it means an analog of a half line in C, is a submanifold with boundary the binding. So initially in the constructions of Murasugi and of Stallings, fiber surfaces were simply pages of some open book. And now we could prove this generalization of Stallings' theorem if you take two summable patched pages of open books. It seems a little long, but it means what? You have two manifolds, on each one of them you have an open book. You choose a page in each part, and you have to choose the patches which have to be identified. You choose them as you want. You patch them. Then the result is again a page of an open book. So, what is a hypersurface associated to the sum? Here the sum is a new ambient manifold. We have put all of this because the construction depends on the choice of n1. So this is a complicated formalism which shows you exactly what are the ingredients. So it is as complicated as a cookbook. If you forget one ingredient, you destroyed what you prepared for dinner. But in this ambient sum, you see that one has a hypersurface, which is the abstract sum of M1 and M2. And that abstract sum appears again as a page of an open book. So this is our first instance of the fact that this generalized operation is a natural geometric operation, like in Gabai's model. We have a second instance of such of Gabai's model in this generality, generalizing work of Weber, Pajitnov, and Rudolph, dated from the year 2002 in dimension 3. They were studying, in fact, surfaces in the three-dimensional spheres which were not pages of open books. It means that if one tries to extend the page to a full open book of the space, one gets obstructions. And in fact, it is always possible to get the simplest kind of obstructions. It means to get a map theta towards the circle S1, which has only Morse singularities. So we decided to study also this situation in general. If you take now pages of Morse open books, this is how we call the situation where again you have a binding, again you have a function theta towards the circle, but you allow a finite number of singularities which are Morse-type singularities. Now if you take two pages which are smooth, which do not pass through the singularities, you do the embedded sum, then you get again a page which will extend to a Morse open book. But what is interesting is that you do not introduce other kinds of singularities. The singularities which appeared before are kept in the sum. So in fact, the general thing is that even if you concentrate doing the sum near a hypersurface, you preserve what lies far from it. And what I want to explain to you now is what's the origin of this phenomenon. What we believe is the most easy way of dealing with Gabai's credo. It is a reformulation of Planck. I showed you intuitively what it is as a direct extension of what existed before. But now, what we want to say is that it's better not to think about hypersurfaces inside ambient manifolds. It's better to work with covortices. And this is what I want to do now. Just pass and think in terms of covortices. So you see the title here is not the importance of covortism, but the importance of co-orientations. Why? Because I present you a classical covortism. Classically, a covortism, since René-Thom at the beginning of the 50s, is a manifold with boundary, but such that the boundary is decomposed into two parts. And one sees the ambient manifold as a covortism between this closed manifold here, which is disconnected, it's the disjoint union of these two blue ones, and the disjoint union of these three red ones. So W is seen here as a covortism between this negative boundary and this positive boundary. So this is a classical covortism. But here there is a slight non-classical assumption. Classically, in general, one looks either at manifolds without speaking about orientations or about oriented manifolds. Another part of what we do is that we explain that you have never to look at orientations. Everything is a problem of co-orientations. So in fact, no ingredient here, no manifold, W, N, P, touch, at no moment you have to ask if they are oriented or oriented. You always have to ask who is co-oriented and in which way. So in fact here you don't have to imagine that W is an oriented object. In my drawing it is. But this is a schematic drawing of a general situation where the covortism goes from some manifolds here to some other manifolds, and the difference between between the two kinds of boundaries is that this part of the boundary is co-oriented such that you get inside W and here you get outside. It's as if water flows inside W and gets out of W. This is a difference. So the negative part is the ingoing boundary and the positive part is the outgoing boundary. And now we change a little the meaning of cobordism. We will have to work with cobordisms like this, where the ingoing and the outgoing boundaries are not closed manifolds, but are like this, are part of the boundary of the cobordism. So here you see that, in fact, in this precise drawing, the ingoing boundary, it's a union of two segments, the blue ones, is part of a connected component of the boundary of W. And in this connected component, you have also the outgoing boundary here. So simply, it's what we call a cobordism with corners. We have, in fact, all the time to work with manifolds with corners, because when you cut, I showed you at the beginning, you have a patch, and if you remove a patch, you create corners. So all the time one has to work with corners. So that's why also the cobordisms are adapted to this continuous appearance of corners. So a cobordism with corners is simply the fact that you give a manifold with boundary, and you take some submanifold of the boundary here, the blue one. It has boundary in general, and another one. You co-orient the first one in this way, in the ingoing way, and the other one in the outgoing way. You may also have parts of the boundary which do not participate in this game. They are not part of ingoing and outgoing boundary. So, from now on, when I will speak or write about cobordisms, they will be cobordisms with corners. I don't want to repeat all the time cobordism with corners.
So in higher dimensional case, you don't impose something to the blue and red submanifolds?
Absolutely nothing.
Here you have disks, but
you impose nothing. You want simply to take W submanifold, you take its boundary. The negative boundary here is simply a submanifold with boundary of the big boundary. Any submanifold with boundary, and this is a disjoint submanifold with boundary. The first one co-oriented inside, the second one co-oriented outside. So this is a category which can be composed like the usual cobordisms, because two such cobordisms can be composed is an outgoing boundary here coincides to the ingoing boundary of the next one. So you have already an operation of composition of cobordisms. So you see that from this viewpoint, cobordisms are more flexible because they begin to show immediately to the eye that they can be composed. And I will show you another operation on them, which is not this immediate composition operation, which is a summing operation which allows to model in the second way the embedded summing we saw before. So the first thing I want to show you is that when working with hypersurfaces in manifolds, it's better in this context to pass to the associated cobordism. So let's see what the associated cobordism of a hypersurface. It's a very classical scheme. In fact, it is in some ways a birth of topology. It comes from Riemann cutting of Riemann surfaces along curves. A curve on a surface is a hypersurface, and Riemann cut along it. And cutting it, one gets a cobordism. So let's see this. So, it is this one. First, I will show you the reverse operation. Take the cobordism and assume you are in the special situation when there exists a diffeomorphism between the incoming boundary and the outgoing boundary. So you will identify them by this diffeomorphism. We call this a mapping torus of this endobordism. The endobordism being a cobordism from a manifold to itself. It means we chose an identification, which means that here the source of the cobordism coincides with the target. And then you get the mapping tokens. And so you see that here the source and the target get now realized at the highest per surface in the mapping tokens. But because here they were co-oriented differently, the two co-orientations blew, and this hypersurface is globally co-oriented inside the manifold. So this is a special condition we have to impose now if we want to study embedded summing. I showed you before that one could do embedded summing of Möbius bands, for instance. A Möbius band in S3 is not globally co-oriented. But a page of an open book is globally oriented. Because you can push globally the page just by moving the argument. So you see that pages of open books are very special, they are exactly like here. So now we have to restrict to come with one more hypothesis. We have a co-orientation not only along the patch, but along the full hypersurface. So just follow this. I show you now the reverse operation, cutting. If you start from this upper part, and you have here a hypersurface, which is properly embedded, which means that its boundary is part of the boundary of the big manifold. Then you can cut it, and you get here, in fact, a cobordism with the ingoing and the outgoing boundaries, incoming and outgoing boundaries which are identical, exactly like before. So this is an endobordism. So I put the arrow here in this sense. I told you that we start from this and you build this. Well, because from the viewpoint of mappings, it is defined like this. In the reverse way, it is multi-valued. In fact, this is a blowing up operation. Here you do oriented blowing up of this manifold along this hypersurface. So in fact, what Riemann was doing, he was doing blowing ups. In fact, in books, people in general don't explain you this, but cutting an object is doing blowing ups. So if also you cook and you have to put a special paper in order to do your preparations, you have to cut it. You blow up. So children blow up all the time. But we don't explain this. So you see that the drawings here are the same. What I showed you before and here. They are reversed. In fact, these are two inverse operations. This shows that it is equivalent to think about a properly embedded hypersurface which is endowed with a co-orientation and about an endobordism in this sense, with an incoming boundary here and the outgoing boundary there. But if you think a little, you see that this object is still not adapted to studying pages of open books. Because a page of an open book is not properly embedded. Its boundary does not arrive at the boundary of the ambient manifold. It is included in the interior. So to arrive at this setting, one has to do something more. Let's introduce just a definition. A Seifert hypersurface is a hypersurface whose boundary is included in the interior and which is globally co-oriented. In fact, the Seifert surfaces using in knot theory are always like this. The global co-orientation is fundamental in order to push the surface outside of itself and to build the fundamental Seifert form. So in this way, we believe that this is a good name for this general type of object. So now, if you start from such a Seifert hypersurface, here it is this curve on the surface. It is co-oriented. The first thing to do is again to blow up. Near the boundary we choose polar coordinates and then you blow up in that just we create boundary. And after creating the boundary here, you see that the initial Seifert hypersurface is properly embedded. And now you can do the initial operation cutting along it. And when you cut along it, you get now a cobordism between them. But you see that here, near the boundary, you have a supplementary structure coming from the fact that you had to blow up the boundary. And this gives you a special kind of coordinates, which is a cylindrical coordinate, which means that near the boundary of the total space, it's like the boundary of a cylinder. And in fact, when you study embedded summing of Seifert hypersurfaces, you may work in fact with such cylindrical coordinates. And the main lemma is that these two operations of passing from a Seifert hypersurface to a cylindrical coordinate and back are in fact inverse from one to the other. And in fact, you get more than a cylindrical hypersurface. The total space is in fact structured when you have a Seifert hypersurface in the following way. Near here, the base of the coordinates, you have a product structure. And the interior complexity projects on some interval here. So you can imagine this as a cylinder projecting on its height segment. And you have a sub-segment here, we call the core, over which all the complexity projects. And the general operation of summing for cylindrical coordinates is in fact concentrated here. If you want to sum such cylindrical coordinates, you have to ensure that in fact you glue the two heights. So both of them are seen as manifolds above the same segments, and the two cores are disjoint. And now when they are disjoint, you see that you cannot here, about where you are not above the core, you can do the patching of the fibers. Here all the fibers are the abstract manifolds which have to be patched. So here you do the patching. But here you don't have a patch on this part. Nevertheless, I showed you that the same operation can be described disymmetrically by removing the patch from one side. Well, here on this one you have a patch. You will remove it here. And here you don't have to remove. You keep there. So you remove here and you go to the boundary. Well, one has to think a little. But on this picture you can see everything. That if you start from open books, you get open books. If you start from inner open books, you get again inner open books with the same kinds of singularities. So here we say that it's the same operation as before. And just, I want to finish rapidly with several questions. First, we call an open book indecomposable if it cannot be written as a sum like this. We would like to find criteria of indecomposability. How to know that some open books cannot be written as this. Second, find criteria, say algebraic. If you take an open book associated to a holomorphic function on a germ of space with isolated singularities, such that the associated open book is indecomposable in this sense. Third, are there natural constructions of singularities theory which show that the open book associated to some pair x3, f3 is the sum of the Milnor open books associated to two other pairs. And then two other questions related to contact structures, but you may find them in the paper which appeared today on arXiv. So I want to conclude in this way. Thank you very much for your attention.
Thank you very much for such a picturesque talk. Are there any questions?
Somehow there are classical surgeries, like Gen surgery, topological natural arm. Would you somehow relate them to your construction?
I hope so. This was our first work in this subject, so as you see, we just tried to do the basic theory of this operation, hoping that it is sufficiently flexible for studying such questions. But for the moment, we did not do anything else than what I told you here, and which is it.
For instance, you can have a, let's say, make, and then you can make a surgery with itself, like the 10th surgery. You take the area there, and then you identify just two pieces from the same length, right? So that you just make this sort of surgery with the manifold itself. And then the question is what do you get? For instance, if you have three manifolds, you can use the enserger and then you know that each pair can be connected, let's say, by this certain operations.
One has to now our way of thinking is that just translate this in terms of coordinates and then use the main picture. And there in the main picture as the operation on coordinates, one sees things. So till now we saw that in that picture things become very clear. But I did not think about this and I'm not able to decide now in 10 seconds.
The another thing, just the geometric net blow up is also somehow could be related to that, right?
What else?
Thanks. I have two questions that you more or less posed in your questions. The first was what kind of application to singularity theory you have in mind, because I'm sure you have some in mind, and I think that's what you were saying there. Yeah, it's very good. The other question is also somehow maybe in your next questions, which is how does this behave in relation to contact structures? Yeah, that's
These are two questions about
yeah.
this.
So in particular, maybe I have to read this carefully, I'm not sure. If you have an open book and the binding has a contact structure which is carried by the open book, and you do this operation,
The first question is to describe exactly what should be the position of the patches with respect to the contact structure, such that the operation extends to an operation of contact structures. And such the result is an open book which supports the contact structure obtained like this. This is the first question.
Beautiful, that was my question.
And the second question would be to find something like an open book supporting the contact structure. The open book is decomposable, but not decomposable as sum of open books supporting contact structures. So that the composability is purely topological, but not contact theoretical. So this is the second question.
Beautiful, thank you.
So if there are no other questions, we thank the speaker again.